the recording now. Or maybe Yossi has already started. And so we have Ellena Moskovsky, one of our organizers, talking about maps, fully simple maps, and topological recursion. So Ellena, feel free to go ahead.
Okay, thanks very much. I'm just going to share my screen. So while I'm doing that, let me reiterate. Well, first, let me say thanks so much for having me speak at this delightful seminar. And I will reiterate what Grace said. Please stop me and ask questions if you're ever unsure about something, because likely if I've explained something terribly, everyone else in the audience is also confused. So please do stop and ask questions. I can't guarantee that I'll keep an eye on the chat, so feel free to just unmute yourselves and just jump in if you have a question. Okay, before I start, I should also say that the research that I will tell you about towards the end of the talk today is joint work in progress with my supervisor, Norman Doe. Okay, so I'd like to start with a motivating question today. So suppose you have a surface, and suppose your surface has some boundary components. So here I'm imagining that someone has come along and cut these polygons out of my surface to create some boundary on my surface. Okay, so we know from the classification of surfaces that we can completely determine this surface by triangulating it, or equivalently by tiling it with polygons. Okay, so on the other hand, a slightly different question we could ask is, in how many ways can we do this? So in how many ways can we tile our surface with polygons? Okay, so if we don't add in any further constraints, there's obviously going to be infinitely many ways that we can do this, because we can just keep adding in polygons to our heart's content. But if we put in some constraints on the number and types of polygons, what we might say their degree or the number of edges that they have, then all of a sudden it turns out that there's a finite number of ways that we can do a tiling with this data. Okay, so let's see an example about how this works. Sorry, just organize myself here. Okay, so suppose I wanted to tile the two sphere with exactly two quadrilaterals, or what we might say two faces of degree 4, where one of these quadrilaterals is a boundary component. Okay, so it turns out that there is exactly 3 ways to do this. Okay, so let me show you what they look like. So the first example looks like this. So we just have a square, and on the inside face of our square, we have our first polygon. So it has sides 1, 2, 3, and 4. And then the outside of our square is our other polygon. So it also has sides 1, 2, 3, and 4. So I should also clarify that here I'm drawing my tiling on the plane, like on my screen, rather than on a sphere, but I'm just imagining that I'm taking my screen and compactifying it, and in that sense, thinking about it living on the sphere rather than living on the plane. Okay, so that's our first example. The other 2 ways that we can do this look like this. So again, in this example, we have our first face is on the interior of this polygon here, and so it has sides 1, 2, 3, and 4. Hopefully you can see my mouse. Sorry, it's a bit shaky. And then
I think I did see your mouse then. I'm not sure if I was.
You did or you didn't?
Didn't.
Well, okay, that might be annoying if you guys can't see it. So you can't see it now? No, I'm getting a lot of head shaking.
I can see a white mouse under exactly.
But it's not moving.
Yeah.
Oh.
Yeah.
Okay.
Now I can see it.
Now it's moving. Yeah.
Okay. All right. Okay. I was using my pen before. Now I'm using my mouse. Okay. Good to know. Thanks for letting me know. Thanks for jumping in. Okay. Okay. So, well, hopefully that made sense before, but just to clarify with this particular tiling here, the interior of this shape is one face. It had sides 1, 2, 3, and 4. And the outside again has sides 1, 2, 3, and 4. Okay, so you'll notice that I counted like both sides of this edge, which might seem a little odd, but you might have also noticed that I did the same thing here. So I counted the inside of this edge, which was adjacent to this interior face, and then I counted the outside of this edge as being adjacent to the outside face. And that's just sort of like a conventional thing that we do that just sort of makes sense. You can think about each of the edges in this tiling as being kind of like half edges, and each half edge is adjacent to a face. They might be adjacent to different faces as they were here, or adjacent to the same face as they were here. Okay, and then the last example is the same sort of idea. So the inside has degree 4 and the outside has degree 4, and it's another tiling of the 2 sphere with 2 quadrilaterals. Okay, so there's an example. And in this particular case, there was exactly 3 ways that we could do this tiling. So, and if you do this with any genus G surface with any specific number of polygons, as long as you dictate how many you want to use and their degree, then you're going to have a finite number of ways that you can do this. And somehow enumerations that have finite number answers generally can be interesting. For example, people who study them might want to ask questions like, what kind of properties do they satisfy? Do they have any structure? Do they satisfy a recursion? Okay, so in this case, mathematicians have found that this particular enumeration is interesting for a number of reasons. I want to tell you what those reasons are, or tell you at least some of those reasons today. But to do that, I first need to define these tilings formally. And the way that we do that is by an object called an ordinary map. Okay, so let me tell you what an ordinary map is. Okay, so you can think of an ordinary map informally, kind of how we've been talking about it, as taking a finite set of polygons and gluing them together along edges until you form a surface. Or more formally, you can think of it as a graph embedded on a compact oriented surface, such that the complement of the graph on the surface is a disjoint union of topological disks. So this condition ensures that what you're gluing together are polygons and not things that are more complicated. Okay, so we also choose n of our faces to be marked faces. And so by faces here, I mean, the complement of the components that you get of the complement of your graph on the surface. Hopefully that makes sense. And these n faces we choose to be marked, we kind of secretly think about them as being our boundary faces, because that makes sense to do that in some contexts, even though we don't formally include it as part of our definition. Okay, so let me show you an example of something that's not an ordinary map. So this graph on this genus 1 surface is not an example of an ordinary map, because if you take the complement of this triangle on this genus 1 surface, you'll get 2 components. One of them is the interior of this triangle, and then the other one is a component that has a handle, so it's not homeomorphic to a disk. So this is not an example of an ordinary map. But on the right here, I'll show you some examples of maps, ordinary maps that are maps. Just scroll down a bit. Okay, so here we have a graph embedded on a genus 1 surface. It has 1 boundary component. Here we have a graph embedded again on a genus 0 surface with 2 boundary components. And here's the example we looked at the start, which has a genus 2, so underlying genus 2 surface has 2 boundary components. Okay, so if you don't take away anything else from this talk, I would like at least for you guys to be able to go away and draw some examples of ordinary maps and enumerate them if that's what you really wanted to do, which you might. And so to do that, you need to know when are 2 ordinary maps the same, or what is the notion of an isomorphism between ordinary maps. And it's just what you imagine, essentially. So 2 ordinary maps are isomorphic if there exists an orientation-preserving isomorphism of the underlying surface that is also a graph isomorphism of the graph that you've embedded on there. And a graph isomorphism is a mapping of the graph that preserves all adjacencies of edges and vertices. Yeah. Okay, maybe now's a good time to pause and see if there are any questions so far.
Is this an orientation preserving homeomorphism? Or an isomorphism?
That is a really good question. I probably do mean homeomorphism. I don't really work in topology, so, so I don't often think about homeomorphisms. Everything's just an isomorphism for me. I probably do mean homeomorphism. That's a good question. But look, yeah, I can clarify maybe at the end of the talk and get back to you, but I'm not 100% sure.
Hi, I have one more question.
Yeah, go for it.
So are we like, can we move this embedded graph like homotopically before we look for this isomorphism? Does that kind of make sense?
Yes, the question makes sense. And I think the question makes sense, and I'm pretty sure the answer is no, if I understand your question correctly. So maybe what I'm about to talk about next will help clarify.
Right, so we have a fixed embedding and it's not up to homotopy or anything.
When you say homotopy, do you mean homotopy of this?
Oh, maybe it's not clear.
I guess what I mean is you embed your graph on the surface, and then after that, if you can come up with any homeomorphism probably of the underlying surface that changes your what your embedding of your graph looks like to something else that you have, then the two things are isomorphic.
Okay.
Yeah, but maybe my next example will answer your question. So maybe I'll talk about that, and then you can let me know if you're still unsure.
Cool, thanks.
Okay, so there's a small sort of, I guess, slightly surprising behavior, which you might not expect from the outset, which is that because you're embedding your graph on an oriented surface, somehow the orientation of your surface gives rise to a kind of what you could think of as a sense of orientation of your of your graph. So let me tell you what I mean by that. Okay, so here I've got an example of two ordinary maps where the underlying graphs are isomorphic. So if you take the graphs away from the surface, they're isomorphic as graphs because they have the same number of edges and vertices with the same adjacencies. But once you've embedded them onto the two-sphere, there's no homeomorphism of the two-sphere that will take you from one of these graphs to the other. And so you can kind of think of this as like the orientation of the surface, which we just choose by convention, gives rise to a sense of orientation of orientation of the vertices, the orientation of the edges about a vertex. So it gives you some sort of notion of moving cyclically around the edges around a vertex. And you'll notice that doing this in the case on this right-hand side gives you something different as when you do it on this left-hand side. So James, does that answer your question?
Yeah, kind of. I think so. So I guess these aren't homotopic in some sense, right? You can't kind of move one to the other continuously.
Yeah, that's right.
Yeah.
Yeah, that's right. You can't.
Yeah.
Yeah,
Okay.
and that's why they're not different in this case.
Right. Okay. Cool. Awesome.
Yeah.
Thanks.
You're welcome. Okay, so mathematician William Tutt was studying these objects back in the 1960s, and he proved that these objects satisfy a recurrence relation, which we now call the Tutt recursion for obvious reasons. Okay, so if you're not really that familiar with recursions, you should at least be able to think of one recursion, which is the recursion for Fibonacci numbers. And if you're not that familiar with recursions, you can just keep this Fibonacci recurrence relation in your head when you're thinking about this, or when I'm talking about this Tutt recursion. The key thing that you have to remember is that you can calculate the next number of your sequence in a recursion by using previous numbers in your sequence. That's the key ID. Okay, so the way that Tutt derived this recursion for ordinary maps was as follows. So the main idea he had was take an ordinary map, choose a boundary face, and remove one of the edges on your boundary face. Then the outcome that you get, so several mutually exclusive things can occur, but the outcome that you get will always be another ordinary map. And it'll be reduced in some sense because it'll have fewer number of edges because you've gone ahead and removed one. So let's see how that works with an example. Let's say I have this example that we had from the previous slide. And I'm going to remove this edge here that's adjacent to this boundary face. So when I do that, the boundary face is going to kind of like fill up that whole empty space that's now one polygon instead of two. And the result is, again, an ordinary map. And it's smaller in a sense because it has fewer edges. And so Tut's recursion is a recursion on the number of edges in your ordinary map. And you can keep following this process until you eventually get back down to some base cases. And from those base cases, you can essentially calculate all numbers of ordinary maps in this way. So this is really quite useful, well, first of all, for calculating, but also because it gives some sort of structure to our problem. Yeah, it gives some sort of structure to our problem, and it helps us calculate all numbers of these maps recursively. Okay, so I'm interested in ordinary maps, but I'm also interested in a very particular subset of ordinary maps called fully simple maps. Okay. So we say that an ordinary map is fully simple if the boundary faces do not self-intersect and are disjoint. So let me tell you what I mean by that. So in this example, well, this non-example here on the left, so there's these two boundary faces that are adjacent along this via this vertex in the middle here. So these two boundary faces are not disjoint. So this is not an example of a fully simple map. For this ordinary map down here, this is not a fully simple map because the boundary face self-intersects itself along this edge. Remember how I said you could think of this as two half edges, and these two half edges are both adjacent to the boundary face, but also adjacent to themselves. So you've got that this boundary face self-intersects along this edge here. So in that case, this is not an example of a fully simple map. But these two diagrams on the right are examples of fully simple maps because the boundary faces don't intersect themselves and they are disjoint in all the cases where it's relevant. Okay, maybe now is also a good spot to stop and see if there are any questions about anything so far. Okay, very good. All right, so suppose I wanted to come up with a Tut-like recursion that governed these fully simple maps in the same way that there was a Tut recursion for ordinary maps. And if I was to try to use the same mechanism, the same idea as Tut did for the Tut recursion, you'd see that I'd very quickly run into trouble. Okay, so let's take this example down here. And try and see what happens if we follow the idea of Tut's recursion. So we choose a boundary face. I'm going to choose this one, and I'm going to remove an edge. So I'm going to choose this one on the right here. I keep forgetting you guys can't see my mouse. So I'm going to choose this boundary face on the right, and I'm going to remove this edge here. So what you'll see what I get looks like this because the boundary face fills up the remaining space. And now this is no longer an example of a fully simple map because now we don't have, well, the map no longer satisfies these two conditions. These two boundary faces are now adjacent. Okay, so we can't use the mechanism that Tut did to get a recursion for fully simple maps in the same way that Tut did for ordinary maps. When Tut did it for ordinary maps, the outcome was always going to be an ordinary map. And so we could write a recursion between enumerations of ordinary maps. But in this case, we follow this recursion and we get that some type of fully simple map is equal to some sum of not only fully simple maps. And so we just can't get a recursion in this same way. Actually, it turns out that the goal of obtaining a Tut-like recursion for fully simple maps has just proven to be really difficult, and the combinatorics is just really hard. And in fact, it hasn't actually been done yet as far as I'm aware. Okay, so my supervisor, Norm, and I have made some progress in this area, but we've used a largely algebraic method to do this. So we've tried to move away from the combinatorics and move into the world of algebra, where we can maybe make some headway in this problem. But we've done that because the combinatorics is so intractable and algebra is a little bit easier to deal with.
Just a quick question, Ellena.
Yeah, go for it.
Is it reasonable to expect that such a recursion actually exists?
Yeah, that's a great question. Yeah, I don't know. Maybe not. Maybe it's not reasonable to expect this. Yeah, or at least one, even if you did come up, like maybe say Norm and I can finish working in our area and we do find a recursion for fully simple maps. We have examples in low genus cases. But if we were to find it in full generality, it's entirely possible that it wouldn't make sense combinatorially, like we just wouldn't be able to prove it combinatorially. So maybe it's not really very realistic to expect that something here, that there is something that you can do here by combinatorics. Yeah, I mean, when I first had this problem, I was like, why don't we just write down a recursion that has to do with fully simple maps and ordinary maps, because sometimes in some cases you end up with ordinary maps instead of fully simple ones, but it's just somehow not that useful. I guess it doesn't really get you anywhere. Yeah, okay.
Thanks.
You're welcome. All right, great. So at this point, it would be completely reasonable if you were still wondering why on earth are we talking about maps, fully simple or ordinary? You know, why are we talking about tiling of surfaces at all? Why is it interesting? Okay, so quite often people find things interesting because of their relationships to other areas in mathematics. And that's definitely true in the case of ordinary maps. So let me tell you why that is. Okay, so perhaps one of the biggest reasons that sort of burgeoned the study of ordinary maps most recently is that the enumeration of ordinary maps is governed by the Hermitian one matrix model. If you don't know what this Hermitian one matrix model is, it's just a particular type of random matrix model. And actually what's more accurate to say is that it's sort of the prototypical example of a random matrix model. And again, if you don't know what random matrix models are, that's okay. All it is to say is that the people who are interested in studying random matrix models are interested in studying the enumeration of ordinary maps, for precisely this reason. It's also through their relationship to random matrix models that map enumerations are related to mathematical physics, and more precisely, so that map enumerations approximate the Einstein action of 2D quantum gravity. So again, this doesn't have to mean anything particularly to you. All it is to say is that physicists back in the maybe, I want to say 60s, 70s, and 80s were studying something called 2D quantum gravity. And in the process of doing that, they were interested in studying this particular integral that I've written down here. And they found that you could approximate this integral by tilings of surfaces of all genus. And so people who were interested in studying 2D quantum gravity ended up being interested in studying map enumerations. Also, unrelated to that, map enumerations are also related to the calculations of very particular quantities in the study of free probability called cumulants. So people who are interested in studying free probability are particularly interested in studying these cumulants, and they then become interested in studying the relationship between ordinary maps and fully simple maps that sort of arises naturally in that process of studying and calculating these cumulants. Okay, so the last reason that I have here, and the one that I'm most interested in, is that the enumeration of ordinary maps is governed by something called topological recursion. So like I said, this is the particular dot point that I'm most interested in. This is what I want to spend the rest of the talk telling you about. Before I do that, I should make one small caveat, which is that when I first wrote this talk, the enumeration of ordinary maps was governed by topological recursion only, but it has since been proven that also the enumeration of fully simple maps is governed by topological recursion. So that was done by two separate groups about 2 months ago, and I'll tell you a little bit more about that. a little bit later on. But before I can do any of that, I need to tell you what topological recursion is. So let me do that now. Sorry. Okay, so as in the title, topological recursion is just a recursion. Okay, so like we've already seen a couple of recursions in this talk already, the recursion for Fibonacci numbers and the recursion for ordinary maps. Even though the definition of topological recursion is necessarily more complicated and a little bit more, what do I say, like the opposite of down to earth, if you, I kind of wanted to bring up these examples of some sort of simpler recursions as something to keep in mind when we're going through the definition, and hopefully it'll help motivate parts of the definition because we can keep in mind the key ideas that any recursion has. Okay, so so here I've got the recursion for Fibonacci numbers and the recursion for Catalan numbers, which you may or may not have seen. But the main ideas that I want to point out and the themes that all recursion have is that you have the recursion itself, which is valid for some numbers, valid from some point onwards, and then you have some base cases. And within the recursion itself, as I said before, you've just got that you can essentially calculate the next number in your sequence by sums and or products of previous numbers in your sequence. And that's the main idea. That's all you really need to keep in mind. So hopefully that will help motivate the slightly more confusing definition of topological recursion. Okay, so topological recursion has some input, then it has its main mechanism, the recursion, which you can think of as just like a big black box sort of, and then it has some output. Okay, so the input that we put into topological recursion is something kind of like a plane curve. If you don't know what that is, it's kind of like an algebraic curve that lives in a plane. And if you're not that familiar with algebraic curves, that's also okay. All you need to remember is that what we have as input basically is these two meromorphic functions, x and y, that are defined from some compact Riemann surface to CP1. So CP1 here is just the complex projective plane, and a compact Riemann surface, well, a Riemann surface is just a surface that looks locally like the complex plane. So all you need to remember is that we just need these two meromorphic functions, x and y, and those comprise most of our input for the topological recursion. So let me just give you an example of what some of these meromorphic functions might look like. So here we've got x of z equals z e to the negative z and y of z equals z, or you can write it in a non-parameterized form as what looks more like an algebraic curve or a plane curve down here as y e to the minus y minus x equals 0. And then I've got a couple of other examples here as well. Okay, so this is our input, these two meromorphic functions. And from this input, we define the base cases that we need for our recursion. So in the case of topological recursion, the base cases are what we would call omega 0,1 and omega 0,2. And these are just defined using our meromorphic functions. Okay, so I haven't told you what these omegas are just yet, but I will in a second when we get to the output. So just hold that thought if you're wondering. Okay, and then we have the main mechanism, which is the recursion itself. Okay, and this is what the recursion looks like. Okay, so as I said, it looks a little bit more complicated than most recursions that we've seen so far, but all you need to sort of, well, I just want to point out the few key things is that on the left we have omega gn, and then on the right we have a sum of different omegas, like combinations of them. And for all the omegas on the right, they are smaller in a sense, and they're smaller specifically in the sense that they are, like their Euler characteristic 2g minus 2 plus n is smaller. So specifically, this recursion is a recursion on the Euler characteristic 2g minus 2 plus n, where these subscripts are the g and n in the Euler characteristic. And you can think of them as like you would in the Euler characteristic, genus and number of boundary components. So there is actually a useful diagrammatic sort of schematic for how this recursion, or a way that you can interpret how this recursion behaves. And it's kind of a little bit more useful to think about it in that way. Okay, so you can think of the recursion as going from the left side to the right side by removing all pairs of pants from a genus G surface with n boundary components in all possible ways. Okay, so here on the left side, we have a surface of genus G with n boundary components. And then if you remove a pair of pants in all possible ways, you get some specific set of outcomes that can occur, that can arise. So one way of removing a pair of pants can look a little bit like this. So it reduces your genus by 1, but it increases your number of boundary components by 1. So the result you get relates to an omega G minus 1 n plus 1. Or if you remove a pair of pants, you can end up with a disconnected surface. And so you need to sum over all possible ways you can do that. And what that means is essentially summing over all possible ways you can split up the remaining genus and remaining number of boundary components. And so this gives you a sum over all possible ways to remove a pair of pants from your surface and end up with 2 disconnected components in your surface. Are there any questions about that and how that works?
You've sort of got this Z1 seems to be special. Is that playing into this somehow?
Yeah, good question, good observation. So the Z1 is special, and it is also special in the recursion up here. So you'll notice that on this, well, you might not, because it's probably not that immediately clear, but so in these omega GNs on the right, you actually don't have any Z1 arising there. So here you have Z2 to Zn, and then here these Zi, Zijs don't contain Z1 either. So it is kind of special in the recursion, and that's why it's also special in the schematic, which represents what the recursion looks like. Yeah. I hope that answered your question. Okay, great. Okay, so that's what the main recursion looks like. The actual recursion itself isn't that important. I sort of just wanted to show you what it looks like, just like I said, to show you the key themes and like the overarching form of it rather than any sort of specific detail. And then the recursion gives us some certain output. And the outputs that it gives us are these omega GNs, which I haven't told you what they are yet. So you get one for all G and N where G is greater than or equal to 0 and N is greater than or equal to 1. And I mean, they are meromorphic differentials, but that is not so important. All that you really need to know is that they contain the data of the problem or enumeration that you're interested in. So basically, you choose some 2 meromorphic functions, x and y, you plug them into your TR black box, the recursion does its thing, you get out these omega GNs, and they store the data of the enumeration that you are interested in. So basically, they calculate the next value in your sequence. It's just a little bit more complicated than that. Okay.
Maybe a really quick question.
Yeah, go for it.
So do these, I guess the omega GNs, do they have any like symmetries as tensors?
Yes. Yeah, they're symmetric in all of its arguments. So
okay. Right.
Yeah, so omega GN has, it's really confusing because they're not really functions, but they are, well, they're not really functions, but they're sort of functions of n variables, and they are symmetric in all of its arguments, which is surprising precisely from what the question Emily asked, where Z1 is special in the recursion. And so it is surprising that the output are symmetric, that, yeah, it somehow didn't matter that this Z1 was special. Yeah, it is surprising, and it is interesting that they are symmetric. Yes, they also satisfy some other properties, like something like, let me make sure that I say this at least approximately correctly. Yeah, so like you can take these omega GNs and expand them in a particular coordinate as a power series, and then the coefficients of like a monomial in your power series, those things satisfy some certain properties as well, like things kind of like polynomiality, which
Okay.
kind of confusing maybe if you don't really know what it looks like, but yeah, they do satisfy some extra properties that are useful as well.
Cool. Interesting.
So in these power series, does it contain any information about like enumerations of things, or is that too good to be true? Like what kind of data is omega GNs? Just I guess I just want some elaboration.
Yeah, okay, so good question. So let me give you maybe an example, and we'll see a little bit more about this when I talk about maybe why TR is interesting. But just to give you like a concrete example of how this works. So if you take as input x of z equals z e to the minus z, which I mentioned before, and then y of z equals z, and then you plug this into TR, and it gives you as output these omega GNs, and you can expand these omega GNs in some particular coordinate, and it gives you a power series. So you expand it around these x coordinates. Where really this is x of z1 to the mu1, x of z2 to the mu2. Just bear with me for a second here while I write this down. X of zn to the mu(n). And the coefficient that you get here is a Hurwitz number, hgn of mu1 to mu(n). So depending on what you use as input, the coefficients do contain enumerative data specifically. And enumerative data for a lot of different, like a variety of different types of problems. So yeah, I'll talk a little bit more about that in a second. So maybe we'll get to that. And then if you still have more questions, we can ask again. Okay, so let's get to it. Why do people care about topological recursion? Which is a great thing to question, a great thing to wonder. Sorry, let me just find my mouse. So let me give you the 3-minute infomercial. Okay, the main reason that people are interested in studying this topological recursion is because of the sheer breadth and variety of problems that it has proven to govern. Okay, so I'll, like for example, well actually first let me tell you what that means. So it means that depending on what like x and y meromorphic functions you use as your input, you plug them into the topological recursion, you get these omega GNs as output, you expand them in this special coordinate, which is sometimes not obvious, and you can get that these power series contain information for any one of these problems, just depending on what x and y you chose as your input. So you might get in as output the enumeration of ordinary maps, which I've already told you is governed by topological co-op, but you topological recursion. But you can also get out Gromov-Witten invariants, Gromov-Witten invariants of CP1 or Gromov-Witten invariants of Toric-Clebauer threefolds. You can get out numbers, intersection numbers on the modulo space of curves, or the volumes defined by Mazzacani of modulo spaces of hyperbolic surfaces. Perhaps these last two might be more interesting for the topologists in the audience. So TR has also been conjectured to govern asymptotics of the colored Jones polynomials, and it has been proven to govern colored Humphrey PT polynomials of torus knots. So we've already got, like, and I've already listed just a few, there's many more examples, and we've already got like a pretty interesting spread and variety of problems here. And like, I mean, what it sort of means is that there's one recursion, like the same recursion that you saw above, that can generate numbers for all of these different types of problems. So yeah, I mean, it's just one of the main reasons that people are interested in studying this, because what does it mean? What does it tell us that these problems can be governed by the same recursion? Does that give us any useful commonality between these problems or some sort of universality? Can it, like, what can we deduce from that information? What can that tell us? And another reason that people are sort of interested in it is because, so kind of like I was telling James before, so like these omega GNs do satisfy some certain properties. And so if you can prove that something's being governed by topological recursion, then you have already some immediate information about your problem. So for example, you can say that your coefficients satisfy this polynomial behavior, or that your omega GNs are symmetric in its arguments, and that might tell you something. So topological recursion and problems governed by topological recursion have many proven and also conjectured properties. So one of these conjectured properties is something called symplectic invariance, which I do want to tell you a little bit about. And hopefully we get to it. I think we should. Yeah, so this was the infomercial. Hopefully that was sufficiently interesting enough to have you all hooked. Okay, so I told you that ordinary maps are governed by topological recursion. So let me tell you exactly what that result says. Let me just figure out first how to find my mouse and move my screen around. Sorry, bear with me while I figure out how to use my own computer. Okay, maps, fully simple maps and topological recursion. Okay, so back in 2007, Ellena and Orenton proved that ordinary maps are governed by topological recursion. Okay, so specifically, they said that if you take these specific X and Y parameterized functions and you plug them into topological recursion, you'll get as outputs omega GNs, and they'll contain the enumeration of ordinary maps in those meromorphic differentials. So here, alpha, gamma, and these uj functions are just expressions that contain data about your non-boundary faces in your ordinary map. They're not too important. Okay, so very recently, well, not that recently, 4 years ago, Elba, Garcia-Felder, and Gaetan-Barreau conjectured that the enumeration of fully simple maps was also governed by topological recursion, where your input data that you use for your spectral curve is what you get is, well, the X and Y that you want are the X and Y for ordinary maps, but swapped. Okay, so it's a very specific relationship between ordinary maps and fully simple maps here, because if you may have recalled from the examples that I gave you before, the X and Ys in those cases don't look anything alike. So this is a very specific transformation, and this swap of this X and Y is an example of something called a symplectic transformation. So it preserves some specific properties. Sorry, what I should say is that it's conjectured to preserve some very specific properties that people are interested in. So people are very interested in studying this symplectic invariance because it's quite mysterious, and people, if it can be proven that it's true, people would be very interested in that because it's useful to have these invariants, that these particular properties are preserved. And so this specific instance of where we have a geometric problem that's governed by TR, we take the X and Y meromorphic functions as input, we swap them, and it turns out that that is also governed by TR, like a geometric problem that's also governed by TR. It would just be a very specific example of a symplectic transformation and might help make us some inroads on this notion of symplectic invariance and whether it's true or not. Okay, so like I said, when I first gave this talk, this was still a conjecture, but it's actually recently been proven by two separate groups. So there's the names of the mathematicians. They actually both found out, both groups found out at the same conference that the other group had had some results in the exact same problem, and they conversed and agreed to publish on the same, like put up their papers on the archive on the same day, which I thought was nice. Well, at least it was good for them. It's not, maybe not so good for me. Okay, so let me spend the last couple of minutes just telling you about the progress that we've made towards this then conjecture, now theorem. So I guess our goal was to prove this, which was, like I said, then a conjecture, that the enumeration of fully simple maps is governed by topological recursion. How do you prove that something is governed by topological recursion? Well, one of the key ingredients that you need is actually some kind of recursion to begin with. So in the case of ordinary maps, you can start with the tight recursion, which I told you about, and then you perform some sort of analytic and algebraic manipulation, and you transform that into the topological recursion. So there's like a semi-standardized sort of procedure that you can follow once you have the once you have sort of a recursion and one other key ingredient that you need. So the first step that we need to prove or to create another proof for this theorem was to start with a to start trying to find a recursion. Okay, so let me explain what's going on here in this diagram. So the overarching idea is that upstairs you have the world of combinatorics, and that's where the tight recursion lives, and that's the world in which we want to find a tut-like recursion for ordinary maps. Okay, and the key idea that my supervisor and I had and that we were working on was to move everything downstairs underwater into the world of algebra. Okay, so the way that we did that was very loosely as follows. So we start with the tut recursion, and then we transform that expression into generating function form and get something that is a differential equation actually. So what we obtain looks something like this, where you have some Vn is a differential operator, and it's acting on some generating function for ordinary maps, and you get that this differential operator acting on this generating function equals 0. So it's a differential equation in terms of this generating function for ordinary maps. So now that we're living in this algebraic world downstairs, in this world, it's much easier to apply particular technique to apply a very particular technique. And so the way that we did that was there is some existing relationships that people had already proved between maps, ordinary maps and fully simple maps. And in this algebraic world, we could transform basically that relationship into a conjugation idea. So we can take the generating function for ordinary maps and apply a conjugation to it and obtain essentially almost identical looking differential equation here on the right, but now it's in terms of the generating function for fully simple maps. So now we have this differential equation in terms of the generating function for fully simple maps. And then from there, we can move back into the world of combinatorics by extracting a certain coefficient from both sides and get a tut-like recursion now for fully simple maps. So that was maybe a lot of details that, like I said, it's not, the actual details themselves are not really that important. Just the overall idea, I would like you to keep in mind or to take away from this talk is that we can move into the world of algebra and then apply this conjugation trick to move from the world of ordinary maps to fully simple maps, and then we can move back into combinatorics to get the recursion for fully simple maps that we're interested in. So this is still a work in progress. We have some low genus, low boundary component numbers like recursion in these low cases, but we're yet to find a general recursion for all sort of general genus and general number of boundary components. That's sort of still a work in progress. And so I think I'll finish there. Thanks very much.
Thanks, Ellena, for the talk.
Yeah, I had a question, a quick one. So how different was their proof towards, did they use this sort of idea of like changing the combinatorial problem to doing some kind of transform and turning into an algebraic problem? Or was it just completely off the wall, different methods like altogether?
So good question. Okay, so one of the groups proved it in a slightly different way altogether. So what they did was they had this like bigger class of combinatorial objects. So instead of just looking at fully simple maps, they looked at these larger things called conjectured maps. And they proved that those conjectured maps were proved by topological recursion, again, by finding a recursion and following the semi-standardized process that I told you about. And then they said, well, hey, fully simple maps are a subset of these. And so they were able to like use some, like switch on and off some parameters to use their proof for, I think they were called conjectured maps. I'm not actually sure now anymore, but it's like switch on and off some parameters for their overarching problem and then use that same proof to prove something for the subset of fully simple maps within that.
So are there features of this particular, for fully simple maps, are there features that wouldn't necessarily, like this sort of proof, maybe it might generalize to these conjectured maps, or is that like not possible? Are there features here that are really particular to the fully simple maps that make this sort of, you know, transform approach work? Like, is it just off the cards, like trying to
it is kind of specific to this problem. So we actually use the relationship between ordinary maps and fully simple maps in this conjugation trick. We have that, like, we can relate them via this conjugation in this algebraic world because of some previous results that people have proved between ordinary maps and fully simple maps. So I think the method is kind of specific to this idea of like ordinary versus fully simple. So it's possible that this, maybe not necessarily to maps, but like to the ordinary versus fully simple idea. So like maybe you could have this dichotomy of ordinary versus fully simple in other settings and then apply the same idea. But as far as I understand, not that I have, like they only came out recently, so I haven't like digested them more fully yet, but as far as I understand, the people who use that method of conjectured maps, I'm not sure this would work in that setting. But so the other group of people that also proved this did use the relationship between ordinary maps and fully simple maps pretty explicitly. So I don't know how exactly, because like I said, I haven't read them completely yet, but yeah, I think they do use this, something very much like this idea, but maybe in a slightly different world. So not using these differential equations sort of thing. But yeah, like I said, I'm still not 100% sure.
Thanks.
We're getting close to the end of time, but if anyone has another burning question they have to ask Ellena, feel free.
I have a question, but it can happen afterwards.
Real quick. So this, you mentioned that this swapping the x and y is like a symplectic transformation or something. So is that to do with the symplectic structure on CP1, or what's happening?
Oh, look, I don't know too much about it, to be honest. All I know is that, let me just write something down a little bit more concretely. A symplectic transformation, so this is just an example one. A symplectic transformation is anything that preserves dx wedge dy. So there could be some underlying, symplectic geometry going on here, but I don't know too much about that world, sorry.
Yeah, that's all right. Me neither, but I imagine it's probably related if it's dx wedge dy, right?
Yeah.
I'm not sure. Yeah, cool.
Probably.
Thanks.
No worries.
Great. Everyone, let's thank Ellena again for a great talk. Thanks, Ellena. We can probably stop recording now, Yossi.